Hi there, folks. Today we're looking at linear inequalities and systems of inequalities. And so we're going to kind of look at these things from the perspective of graphing, but in two variables. So we're going to graph an inequality in two variables with x and y, see what that looks like, and then see how that translates into a system of inequalities when we have more than one of those things, okay? So the first part of this is we're going to graph the linear component of the inequality. Essentially, we're going to ignore the inequality sign and just graph whatever line it presents if it was an equal sign, okay? The big difference is when we graph that line, we have to decide whether to use a dotted line or a solid line, and we do that based on whether or not there's an equal to condition, okay? So if there's no equal to condition, we use a dotted line, and if there is an equal to condition, we use a solid line. And that's very similar to the concept of using an open dot versus a closed dot. You know, when we graph these things on a number line with no equal to condition, we use an open dot. It's essentially saying that spot is empty. That point doesn't count, all right? It's not part of our shaded region. As opposed to a filled in dot, that solid dot, okay? That means that point is included. It's part of the shaded region, okay? It counts as one of the values, all right? The dotted line and the solid line signify the same thing, okay? The dotted line is essentially an invisible line that doesn't really exist. It's not really there. It's a boundary where those points don't count, all right? A solid line means that those values are part of the answer. They're part of the shaded region. They count towards this inequality, okay? And then once we have that line established, we're going to shade one side or the other. Just like we did on the number line, open dot, closed dot, shade one side or the other. Now it's solid line or dotted line, shade one side or the other. And we can use test points to determine which side we're going to shade, okay? For example, if I look at something like this guy, we talk about the linear component of this thing. If I were to just kind of ignore the fact that this is an inequality, I would have y equals a 2x minus 1. And we know how to graph y equals a 2x minus 1. That's in slope-intercept form. It's got a y-intercept of -1, which I can plot right here. It's got a slope of 2, so that's up 2 over 1, up 2 over 1, or down 2 back 1. But now instead of just drawing a line, I have to decide, okay, this was an inequality. Do I use a solid line or a dotted line? And when we look at this thing, it's y is less than or equal to. So because of that equal to condition, I use a solid line here. Okay, so I connect these with a solid line. But now I'm going to shade one side or the other. Notice my graph is broken into two pieces. Just like when I plotted an open dot or closed dot, the number line was broken into two pieces, and I shade one side or the other. Now this entire graph is broken into two pieces. We're just in two dimensions now. So I need to decide, am I going to shade this thing over here, or am I going to shade this thing over here, all right? And so to do that, I just have to choose a test point. And you can probably look at this thing and say, well, just like we did with number lines, we were able to figure out based on the inequality symbol which side to shade. We can kind of do the same thing here if it's in the right format. When it's in y equals mx plus b format, we can look at this and say, well, we want to be less than this line. It says y is less than or equal to, so I'm going to shade below the line, all right? But again, choose a test point, and you could choose any point. If I choose something like 0, 0, plug 0, 0 in here, watch what happens. I get 0 is less than or equal to a -1. And when I look at that statement, that is a false statement. 0 is not less than or equal to -1, which means 0, 0 doesn't work as an ordered pair, which means I'm on the wrong side of the line, okay? This works by process of elimination. I don't need to test the other side. If this side doesn't work, the other side is the one that has to work, okay? And we arrived at the kind of the same conclusion when we kind of looked at this thing from the perspective of just saying, hey, less than means below the line, so I would shade over here, okay? And as you get good at these, you can probably figure out which side to shade without testing a point. But again, it depends on the format, all right? In this format, y is less than or equal to, yeah, I can see that I want to be below the line, okay? But in certain other formats, we might need to test a point, okay? That's why it's available. If I look at something like this guy, same kind of thing. If I think about the linear component of this thing, it would be y equals a -x plus 3, which is a y-intercept of 3. It's right here. And a slope of -1, down 1 over 1, down 1 over 1. And I went ahead and used my slope to plot a bunch of points here. But then as I look at this thing, it says y is greater than. There's no equal to condition, so I use a dotted line this time. Well, what I have established right now is a dotted line. I could leave it the way it is. Most students prefer putting little dashed lines here, so they like to fill it in like this because it's a little bit easier to see, all right? So dashed line, dotted line, either way. I could have left it as dots. That would have been fine, all right? But this is a little bit easier to see, a little bit easier to kind of visualize. And now I just need to decide, do I shade above this line or below this line? Well, look at the format. It says y is greater than, so I want to shade above the line, so I can shade that up here, okay? And again, that was without testing a point. I was able to kind of look at that and say, well, based on the format, I can go ahead and shade over here, all right? The other option is to choose a test point if I choose 0, 0, and I almost always choose 0, 0. The only time you can't choose 0, 0 is if the line goes through 0, 0, okay? Because I already know what's happening on the line. I already know whether the line works or doesn't work based on solid or dotted. I have to choose a point that's not on the line, okay? So choose 0, 0 when you can. So 0 is greater than 3 is what I get. And once again, that is a false statement. So 0, 0 doesn't work, which means none of the points on that side of the line work. I shade the other side of the line, okay, which we kind of already established here, okay? If I look at this guy, once again, if I think about this in terms of a linear function, and I ignore the fact that it's in an equality, if I just look at this as an equal sign, think about the way you would graph this thing. You might solve for y and put this in slope-intercept form, but most of us would probably just do x and y intercepts. We would kind of look at this and say, hey, if I plugged a 0 in for y, x equals a 2. So that's the x-intercept. It's 2, 0. If I plugged a 0 in for x, y would equal a negative 3. That's the y-intercept. And I can use those 2 points to graph this thing. Ready? 2, 0 is right here. 0, negative 3 is right here. I even have the slope at this point, up 3 over 2, so I can continue that pattern in order to graph this thing. Okay? And now I look at it and say, okay, there's a less than symbol, but there's no equal to condition, so use a dotted line here. Again, I could leave it the way it is, but most students prefer to kind of fill this in with more of a dashed line. Okay? Because it's easier to see, all right? We tend to have a little bit more trouble when we just leave those points, especially in this one because they're spread so far apart. And now I look at this and say, okay, I want this to be less than, well, this isn't in the right format to make that determination. See, it says 3x minus 2y is less than 6, all right? But that doesn't tell us about the line itself because this is in standard form. See, before it was saying, hey, y is less than or equal to, or greater than or equal to, or less than or greater than. And so when we're talking about y, when y is by itself, we can make that determination of above the line or below the line because that's what y is talking about. It's talking about the up and down. It's talking about above or below. Because this one doesn't have y by itself, I can't just use the less than symbol and shade below the thing, all right? This is where I'd want to use a test point, okay? And so if I choose the point 0, 0 once again, if I plug 0, 0 in here, I get 0 is less than 6. Well, that's a true statement. 0 is less than 6, which means 0, 0 works, which means all the points over there work. So I shade this side of the line. Okay? And when we look at that thing, the less than symbol usually leads us to shade below the line. But again, that's only when y is by itself because y is telling us above or below. Is y less than or greater than? Okay? And the other option here is to rearrange this thing. If I were to take this equation, this inequality, I could put it in slope-intercept form first, and some of you might prefer to do this. I would subtract the 3x, and now I divide by the negative 2. And when I do that, I have to flip the inequality sign. That's a positive 3 halves x minus 3. And now I can see the line, y-intercept to negative 3, that's what I have. A slope of 3 over 2, that's what I have. Y is greater than that line, I shade above. Okay? And so we can see in the process of getting y by itself, the inequality sign changed. Okay? So you can only use that shortcut of above or below when y is by itself. Okay? Because y is the above or below, is the up and down. Okay? So if y is by itself, we can use that shortcut. If it's in another format, like standard form, use that test point. Okay? if I look at something like this guy, once again, if I ignore the fact that this is an inequality, if I looked at it as if this was just an equal sign, put in my little thought bubble here, something to think about. If I had this, I would graph the absolute value as a V shape, and you can think about it shifting left, right, up, and down, and stretching and shrinking, and opening up or down. Well, I'm going to use the shortcut here and just say, okay, the vertex is 2, -4. Remember, opposite of this guy just as it is. And then I can tell that this thing opens down because the A value is a negative, and the slope, quote unquote, is going to be kind of like a 1 in each direction. Okay, that's my shortcut for graphing these, and so I plot that. Ready? 2, -4. It's right here. It opens down with a slope of 1 in each direction. Okay, and really it's a slope of 1 and -1. That's kind of like slope. And now I just have to decide, is this a solid line or a dotted line? Well, there's no equal to condition, so it's a dotted line for each of these. And I'm still in that situation where do I shade above or below? But that can be a little bit confusing at times because we have kind of two lines that shape this V. Well, if you still think about it, and I would just go to the vertex and think about above the vertex or below the vertex, all right? And really that's a question of outside the V or inside the V. And once again, if you look at this as Y is less than that V, so below the V, so below the vertex, we're going to shade inside this thing. Okay? And we can still do the test point, all right? And sometimes that'll be beneficial. If I plug 0, 0 in here, I get Y is less than. If I plug a 0 in, 0 minus 2 is a -2. Absolute value, that is 2. Sorry, I put Y. This should be a 0. Crazy guy. Sorry, so -2 inside the absolute value. Absolute value, that is +2 times the negative is a negative, and then minus the 4 is a -6. And if you had trouble plugging that in your head, okay, that's okay. Take it off to the side and do it. But it says 0 is less than -6, which is false. 0, 0 does not work, so I shade, and again, I was testing a point on the outside of the V, so I must shade inside the V. Okay, it's that process of elimination. If I look at this guy, I'm not even going to write the linear component this time. Ready? Let's go right to the vertex. The vertex is 2, -2. This thing opens up because the A value is positive, and the slope kinda is like a 1/2. Okay, that's our shortcut for graphing these. And now it opens up with that slope of 1/2. And now I just need to decide, dotted line or a solid line? Well, there's an equal to condition. So I use a solid line. And now inside the V or outside the V, I want to be greater than this thing. So that's above. So just use the vertex as kind of a point to go off of. Say above the vertex or below the vertex, greater than is above. So that's going to be shaded inside this V. Okay? So we can use that same shortcut, but only when Y is by itself. Okay? And if you want to test a point, test something like 0, 0. If I plug 0, 0 in here, I get 0 is greater than or equal to, let's see, 0 minus 2 is a -2. Absolute value, that is 2 times 1/2 is a 1. Minus 2 is a -1. 0 is greater than or equal to -1. That is a true story, so I shade where 0, 0 is, which is inside the V. Okay? All right, let's talk about systems of inequalities this time. Really, systems of inequalities, this is kind of like an and inequality. We're looking for the overlap. Okay, I'm going to graph both of the linear inequalities. I'm going to see where each of those would be shaded. But then for the system of inequalities, I'm only going to shade where those regions would overlap. Okay, so I have to shade the appropriate region. So once again, I'm just graphing the linear component using that solid line or a dotted line. And then I'm going to shade the appropriate region. Okay, for example, if I look at something like this guy, that first one, I've got a y-intercept of 2. And a slope of 2, so up 2 over 1, up 2 over 1, down 2 back 1. And then once again, I need to decide, is this a solid line or a dotted line? Since its y is greater than or equal to, I've got that equal to condition, I'm going to use a solid line. And then I move on. I'm not going to do any shading yet. All right, I move on to the next one. I say, okay, I've got a y-intercept of -1. And I've got a slope of -1/2. That's down 1 over 2, down 1 over 2, or up 1 back 2. There's no equal to condition this time, so I use a dotted line. And once again, I'll use a little dashed line here. It's easier to see. It helps me see all my different regions. And so now when I look at this thing, I really have 4 regions on this thing. 1, 2, 3, 4. Okay? And so now the graph is broken into 4 pieces. I'm still just going to shade one of those pieces, all right? So I'm going to shade one of these pieces. I just need to decide, all right, which one of these I'm going to shade. And it's the section where the two of these inequalities would overlap. And so as I look at each of these individually, if I looked at just this guy, if I look at this first one, greater than that solid line, so above that line would be these 2 sections right here, okay? It would be sections 1 and 4. All right, so that kind of narrows it down to 1 and 4. If I looked at the other line, the dotted line, it says I want to be less than that line, which is down here. Now it's down to sections 3 and 4. And so if I ask the question, hey, if I shaded those areas, if I shaded 1 and 4 for the first line, and I shaded 3 and 4 for the second line, which section do they have in common? Which section would get shaded twice? Where do those sections overlap? And the answer is section 4. So that's the only one that I shade, okay? And once again, I used the shortcut that we've been talking about to determine which side to shade. You could also test a point. And once again, 0, 0 is a great point to test, but you have to look at them each individually. If I look at 0, 0 for the first line, it's going to be false, which once again narrows it down to sections 1 and 4. If I look at 0, 0 for the second line, it's also going to be false, all right, which narrows it down to sections 3 and 4, which once again tells me which section to shade, okay? So it's that idea of plugging in the point and then using process of elimination, all right, to figure out which sections it gets narrowed down to until I find the overlap, okay? If I look at something like this guy, once again, I'm going to plot each of these. So the first one has a y-intercept of 1 and a slope of 3 over 2, so up 3 over 2, up 3 over 2. Again, there's no equal to condition this time, so I'm going to use a dotted line. The next one, I have a y-intercept of negative 3 and a slope of negative 1/2. There's an equal to condition, so I'm going to use a solid line for this one. And now, once again, I need to decide which of these sections it's going to be. Let's see, 1, 2, 3, 4. Okay? And so as I look at this thing, again, I can use my shortcut because of the format. The first line, the dotted line, I want to be less than that line, which narrows it down to sections 2 and 3. See, if I was just graphing this first line, that dotted line, both of those sections would be shaded. Okay? The next one would be less than or equal to the solid line. Well, less than that line, I would end up shading sections 3 and 4. Okay? If I only had that second line, if I only had the solid line, everything in sections 3 and 4 would be shaded. So now the thing they have in common, well, that's section 3. That's where the shading would overlap. Okay? And the reason I label these and write them down off to the side is because that's a lot easier than shading those entire 2 sections and then trying to pick apart and see where those sections overlap. And then I'd have to do a bunch of erasing. It would be a mess. Okay? If I look at this one, once again, I'm going to plot this thing. They're both in standard form, so the easiest thing to do is to use the x and the y-intercept. So if I look at that first one, if I plugged a 0 in for x, the y-intercept would be a 3. If I plugged a 0 in for y, the x-intercept would also be a 3. So now I can establish this line. Well, it's got a slope of 1. Or sorry, negative 1. And now once again, there's no equal to condition, so I'm going to use a dotted line. And again, I use these dashes. It makes it a lot easier to see. The next one, also in standard form, I'm going to use the x and the y-intercepts. If I plug a 0 in for x, the y value is a negative 3. That's the y-intercept. If I plug a 0 in for y, the x-intercept would be a positive 2. And now once again, I have the slope of this thing. I can keep going. There's an equal to condition this time, so I use a solid line. And now I got to decide which section to shade. And see, this might be a little bit trickier because they're not in the right format for using that shortcut. So I choose a point. And watch, I look at each of these one at a time. So if I look at this first one, if I plug a 0, 0 in here, I get 0 is greater than 3. Okay? And that's false. That doesn't work, which means if I'm only looking at the dotted line, I've now eliminated everything below that line. So I've eliminated sections 3 and 4, which means for that first line, I would end up shading sections 1 and 2, okay? And so again, you have to just visualize this without the solid line here. If I only had the dotted line, I would shade everything above that line because I got a false statement for that point, okay? And that's sections 1 and 2. If I look now at only the solid line, if I plug 0, 0 into this guy, I get 0 is less than or equal to a -6, which is also false. Okay, that's not true. So if I was looking at the solid line, okay, 0, 0 didn't work, which means nothing above that line works. It means sections 1 and 4 don't work. I would end up shading below that solid line, which is sections 2 and 3. Again, if I'm ignoring the dotted line, all right, 0, 0 didn't work, I would shade below that line, which is sections 2 and 3. So now the section they have in common is section 2. So that's the only one I shade. Okay, that's where these would overlap if I graphed each of them. All right, and it's that idea once again of plugging in values using process of elimination. All right, determining which sections each of these would shade individually, and then determining the section that they share. Okay.